Good afternoon, students. This is Arvind, Assistant Professor, Department of DBSIT Kavali. So, in the previous class, I discussed about some effects of harmonics on pitch factor, distribution factor, winding factor, and induced EMF, and line EMF, line voltage, and some numerical problems we discussed in the previous class. And now, in this class, I am going to discuss uh, armature reaction or parameters of armature winding. Okay, so coming to the first, that is parameters of armature winding. So there are three important parameters of armature winding. They are armature resistance, that is indicated with the letter Ra, and armature leakage reactance, that is indicated with the letter XL, and reactance corresponding to armature reaction, that is XAR. So these are the three important parameters of armature winding. Okay. So first we will see the armature resistance, and next we will see armature leakage reactance, and next we will see reactance corresponding to armature reaction. Okay, coming to the first, armature resistance. So here every armature winding has its own resistance. You already know this point. So every armature winding has its own resistance. So here the effective resistance of an armature winding per phase. So actually we are using three phase. So here I am taking the effective resistance of an armature winding per phase is Ra per phase. That is the armature resistance per phase. So here the armature resistance is measured by applying known DC voltage and measuring the direct current through it. Okay, the armature resistance is measured by applying known DC voltage and measuring the direct current through it and measuring the DC current through it, DC through it. Okay, next, what is meant by the armature resistance means the ratio of applied voltage to measured current. The ratio of applied voltage to measured current is the armature resistance Ra. Okay, but due to skin effect, the effective resistance under AC is more than DC resistance. Okay, but due to skin effect, the effective resistance under AC is more than DC resistance. How much value we have means I will discuss here. So effective resistance under AC is 1.25 to 1.75 times of the DC resistance. Okay, effective resistance under AC is 1.25 to 1.75 times of the DC resistance. Okay, while measuring the armature resistance, it is necessary to consider how the armature winding is connected. Okay, whether it is a star or delta connection. Okay, so here I am taking two cases. One is and another one is for delta connection. By using those connections, I am discuss armature resistance. Okay, so here consider a star connected armature winding first. So it is shown in this figure. So here this is the star connection of armature winding. So here I am taking three connections R, Y, B, and each winding consists of resistance Ra. Here I am inserting a voltmeter across R and Y phase, that is V. It consists of the DC voltage VDC. Okay, the B terminal is not connected to the voltmeter. So coming to this one, so when the voltage is applied across any two terminals of the armature winding. Okay, so when the voltage is applied across any two terminals of the armature winding, okay, that means if you observe this diagram, so here the voltage is applied across R and Y phase. Okay, that is R and Y terminals. In between R and Y terminals, I am inserting the voltmeter. So here when the voltage is applied across any two terminals of an armature winding, then the equivalent resistance is the series combination of two resistance of two different phase windings. Okay, the equivalent resistance is the series combination of two resistance of two different phase windings. That is, here the voltmeter is connected across R and Y phase. So here I am calculating the resistance across R and Y phase, that is RY is equal to resistance between R and Y terminals. So here it is a series combination of two resistances. That is, here the resistance is adding. So here Ra plus Ra, that is equal to 2Ra. So where Ra is armature resistance per phase. So Ra is equal to, from this one I am writing Ra is equal to RRY by 2 ohms per phase. So here RRY is the resistance between R and Y terminals. So that is from the above equation I am writing RA is equal to R suffix RY by 2 ohms per phase. In star connected alternator, the armature resistance per phase is half of the resistance observed across any two line terminals. Okay. So in star connected alternator, the armature resistance per phase is half of the resistance observed across any two terminals, that is RY. Okay. And next, coming to the delta connected alternator. So here the diagram represents the delta connected alternator. So here I am taking three terminals R, Y, B. So here also I am inserting voltmeter across two terminals, that is R and Y phase. So the voltmeter gives the voltage reading, DC voltage reading. Okay. So coming to the explanation. So here when the voltage is applied across any two terminals, then one phase winding appears in parallel with the series combination of other two. So you already know this connection. So here one phase winding appears in parallel with series combination of other two. Okay, hence the equivalent resistance across the terminals is parallel combination of the resistance RA and 2RA. That means here one phase winding appears in parallel with the series combination, that is RA plus RA, 2RA, and this RA is one phase winding appears in parallel, that is RA is parallel to 2RA. So here therefore the resistance across R and Y terminals is RRY is equal to RA is parallel to 2RA ohms per phase. So that is equal to after simplifying the parallel connection, that is RA is parallel to RA, we have 2 by 3 RA. From this one I am writing RA is equal to 3 by 2 into R suffix RY. That is the resistance of armature winding, that is RA is equal to 3 by 2 RRY. So thus in delta connected alternator, resistance per phase is to be calculated from the equivalent resistance observed across any two line terminals. Okay, that is for the delta connection and star connection. So we have the armature resistance value. For the star connection we have RA is equal to 2RA, and for 2 in 1 by 2 RRY, and in the delta connection RA is equal to 3 by second of RRY. Okay. And next coming to the armature leakage reactance. This is the second parameter of the armature winding. So previously we discussed about armature resistance, that is the first parameter of the armature winding. And coming to this one, this is the armature leakage reactance. This is the second parameter of the armature winding. So coming to this one, so here when armature carries a current, okay, when armature carries a current, it produces its own flux. It produces its own flux. Okay, some part of this flux completes its path through the air around the conductors itself. Okay, some part of this flux completes its path through the air around the conductors itself. So such a flux is called leakage flux. You know already this one. So some part of this flux completes its path through the air around the conductors itself. Such a flux is called leakage flux. So if you see this diagram, so here I am taking one slot. So it consists of current carrying conductor that is indicated with a circle with the X mark, that is into mark. That is the current carrying conductors, and surrounding that one we have three circles with the dotted lines and with the arrows. So this is the leakage flux. Okay. So what is meant by leakage flux? Some part of the flux completes its path through the air around the conductors itself. Such a flux is called leakage flux. That is indicated in this diagram. Okay. And next, this leakage flux makes the armature winding inductive in nature. Okay. This leakage flux, what we have in this diagram, that leakage flux makes the armature winding inductive in nature. So winding possesses a leakage reactance. Okay, so armature winding possesses a leakage reactance in addition to the resistance. In addition to the resistance, you already know the armature winding consists of its own resistance. So in addition to that one, we have leakage reactance. So if inductance is large, that is L is large, is the leakage inductance of the armature winding per phase, then leakage reactance per phase is given by XL is equal to 2 pi FL ohms per phase. 2 pi FL. So here F is the frequency and L is the leakage inductance. Okay, and XL is the armature leakage reactance. Okay, and next, the value of leakage reactance is much higher than the armature resistance. Okay, the value of leakage reactance is much higher than the armature resistance. Okay, similar to the DC machines, the value of armature resistance is very small. Okay, similar to the DC machines, the value of armature resistance is very small. Next, coming to the, up to now we discussed about two parameters of armature winding. One is armature resistance and another one is armature leakage reactance, and we have another one, third one is armature, the reactance corresponding to the armature reactance. So to explain that one, first we will see the armature reaction concept, and after completion of the armature reaction, we are going to discuss the third parameter of the armature winding. So first we will see the armature reaction. So what is meant by armature reaction? So when the load is connected to the alternator, the armature winding of the alternator carries a current. Okay, when the load is connected to the alternator, the armature winding of the alternator carries a current. Okay, so every current carrying conductor produces its own flux. Okay, every current carrying conductor produces its own flux. So armature of the alternator also produces its own flux. Okay, so when carrying a current, that also when carrying a current only. Okay, so there are two fluxes present in the air gap. So one due to the armature current, while second is produced by the field winding. That is called main flux. Okay, the flux produced by the armature is called armature flux. Okay, the flux produced by the armature is called armature flux, and the flux produced by the field winding is called main flux. So the effect of armature flux on the main flux affecting its value and distribution, and the distribution is called armature reaction. So this is the armature reaction. So effect of armature flux on the main flux affecting its value and the distribution is called armature reaction. Okay, so the effect of armature flux not only depends on the magnitude of the current flowing through the armature winding, but also depends on the nature of the power factor of the load connected to the alternator. Okay, so the effect of armature flux not only depends on the magnitude of the current flowing through the armature winding, but also depends on the nature of the power factor of the load connected to the alternator. So actually we have the power factor, we have nature of the power factor of the load connection is, we have three. So unity power factor, lagging power factor and leading power factor. So now we will study the effect of nature of the load power factor on the armature reaction by using those three. Okay, firstly we will see the first one, that is unity power factor load. So for that one we have to consider a purely resistive load. Okay, a purely resistive load connected to the alternator having unity power factor. Okay, so if you see this diagram, so here this gives the relation between flux of field winding and armature winding, and voltage per phase and armature current per phase can be shown in this phasor diagram. So this is the diagram we are taking. So that is, consider a purely resistive load connected to the alternator having unity power factor. So as induced EMF E phase drives a current of IA phase and load power factor is unity, that means E phase and I phase are in phase with each other. So you already know this one. So induced EMF E phase drives a current of IA phase, that is armature current, and load power factor is unity. So at that time we have E phase and I phase are in phase with each other. So if phi F is the main flux, that is the field flux. Okay, phi F is the main flux produced by the field winding. He is responsible for producing E phase. Then E phase lags phi F by 90 degrees. Okay, here the main flux produced by the field winding, that is phi F, is responsible for producing E phase. Then here E phase lags phi F by 90 degrees. Now current through armature IA produces the armature flux, that is phi A. Okay, now current through armature IA produces the armature flux, say phi A. So flux phi A and IA are always in the same direction in the unity power factor load. Okay, so here we have two diagrams. On the right side we have the armature reaction concept. So here I am taking two poles. One is north pole and another one is south pole. Here the characteristic diagram is drawn between flux and time t. Flux and time. So here it is a sine wave. So it consists of main flux and armature flux. Okay, this thick sine wave gives the main flux and this dotted lines. So if you observe this diagram, some dotted lines waveform is also there. That is the half sine wave. So this sine wave is gives the armature flux wave. Okay. So on the left side we have the phasor diagram. So this phasor diagram gives the relationship between flux of field and armature winding and voltage, that is E phase, induced EMF per phase and armature current per phase. Okay, so this is for the unity power factor means. So here the flux, the main flux and armature flux is perpendicular to each other. Perpendicular to each other, that is exactly 90 degrees. And here the voltage and current, that is E phase and I phase, are in phase with each other. Both are in the same phase. Okay. So this is for the unity power factor. And next, so from the phasor diagram, it can be seen from the phasor diagram that there exists a phase difference of 90 degrees between the armature flux and main flux. So here armature flux, this is the armature flux, this vertical line, and this horizontal line gives O and phi F, 0 and phi F and 0 and phi F. This gives main flux and armature flux. So here the phase difference between these two fluxes is 90 degrees, exactly 90 degrees. There is a straight line. Okay. Next, the waveforms for the two fluxes are also shown in the figure. That is on the right side we have the waveforms of the two fluxes, that is armature flux and main flux. So from the waveforms, it can be seen that the two fluxes oppose each other on the left half of the each pole. Okay, the two fluxes oppose each other on the left half of each pole while assist each other on the right half of each pole. Okay, so if you observe this waveform, so here the two fluxes are assisting each other like this, and the two fluxes are opposing each other like in the dotted line. Okay, so here hence average flux in the air gap remains constant, but its distribution gets distorted. Okay, average flux in the air gap remains constant, but its distribution gets distorted. Okay. Next, hence such distorting effect of armature reaction under unity power factor condition of the load is called cross magnetizing effect of armature reaction. Okay. So such distorting effect of armature reaction under unity power factor condition of the load is called cross magnetizing effect of armature reaction. Due to such distortion of the flux, there is small drop in the terminal voltage of the alternator. Okay, due to such distortion of the flux, there is small drop in the terminal voltage alternator. And next coming to next one, that is zero lagging power factor load. Zero lagging power factor load. So here in this case, I am considering a purely inductive load. So in the previous case, for the unity power factor, I am taking resistive load. Here in this case, I am taking purely inductive load connected to the alternator having zero lagging power factor. Zero lagging power factor. So this indicates that IA phase, that is the armature current per phase, driven by the E phase, that is the induced EMF per phase, lags E phase by 90 degrees. That is the IA phase lags the E phase by 90 degrees, which is the power factor angle is phi. Okay, so here the induced EMF E phase lags the main flux phi F by 90 degrees, while phi A is in the same direction of the IA. Phi A and IA are in the same phase, and E phase lags main flux, that is phi F by 90 degrees. So the phasor diagram and waveforms are shown in the figure. So here, this one. This is the waveforms of the two fluxes, that is armature flux and main field flux. Okay, this is the phasor diagram. Okay, next, so it can be seen from the phasor diagram that the armature flux and main flux are exactly in opposite direction to each other. Okay, from the phasor diagram, the armature flux and main flux are exactly in opposite direction from this one. So this is the main flux and this is the armature flux. Both are in the opposite direction. Okay, so here we have the armature current and here we have field current. Okay, in between we have this one. So here, so armature flux tries to cancel the main flux. Why? Because these two fluxes are opposite to each other. Okay, so armature flux tries to cancel the main flux. Such an effect of armature reaction is called demagnetizing effect of armature reaction. So in the previous one, that is the unity power factor load, we have the cross magnetizing effect. Here we have demagnetizing effect of armature reaction. Why? Because armature flux tries to cancel the main flux. Okay, that's why such an effect of armature reaction is called demagnetizing effect of the armature reaction. So as this effect causes reduction in the main flux, okay, the terminal voltage drops. Why? Because the terminal voltage drop means reduction in the main flux. So this drop in the terminal voltage is more than drop corresponding to unity power factor load. So if you observe this waveform, we have two. So this thick line gives the main flux waveform and this dotted line gives the armature flux waveform. Okay, so if you observe this phasor diagram, so here the main flux and armature flux are opposite to each other. So one is in the one direction and another one is in the one direction. So here it lags the induced EMF by 90 degrees. Okay, so here, as this effect causes reduction in the main flux, the terminal voltage drops. So this drop in the terminal voltage is more than the drop corresponding to unity power factor load. Okay. And next, so consider a purely capacitor load, that is for the leading power factor. So for the unity power factor, we are considered resistive load, and for the zero lagging power factor, we consider inductive load, and for the zero lagging power factor load, we are considering purely capacitive load that is connected to the alternator having zero leading power factor. This means that armature current per phase, that is IA phase, driven by E phase, leads E phase by 90 degrees. That IA phase leads the E phase by 90 degrees, which is the power factor angle phi. So here induced EMF E phase lags phi f, that is the main flux, by 90 degrees, while IA phase, that is the armature current per phase, and IA phi a, that is the flux per phase, armature per phase, are always in the same direction. Okay, so here I am taking the phasor diagram and waveform similar to the previous two. So on the right side we have waveforms of two fluxes, and on the left side we have the phasor diagram. Okay, so this one. So here we have the two waveforms. So the thick waveform gives the main field flux, and the dotted lines gives the armature flux, and on the left side we have the phasor diagram of the main flux and armature flux. So here the main flux and armature flux both are in the same direction. Okay, same, but here it leads the E phase, IA phase leads the E phase by 90 degrees. So this one. And coming to, so it can be seen from the phasor diagram and waveforms shown in the figure, the armature flux and main field flux are in the same direction. That is, they are helping each other. So this results into the addition in main flux. Okay, such an effect of armature reaction due to which armature flux assists the field flux is called magnetizing effect of the armature reaction. So in the unity power factor load we have cross magnetizing, and in the zero lagging power factor we have magnetizing effect, and in this one we have, that is the demagnetizing, and in this one we have magnetizing effect of the armature reaction. Okay. And next, as this effects adds the flux to the main flux, that is greater EMF gets induced in the armature. Okay, as this effects adds the flux to the main flux, that means greater EMF gets induced in the armature. Hence, there is increase in the terminal voltage for leading power factor loads. Okay, there is increase in the terminal voltage for leading power factor loads. For intermediate power factor loads, that is between zero lagging and zero leading, the armature reaction is partly cross magnetizing, okay, and partly demagnetizing for lagging power factor loads. For zero leading power factor, armature reaction is partly cross magnetizing. Partly demagnetizing means for lagging power factor loads or partly magnetizing of leading power factor loads, okay. And next, armature reaction reactance, that is XAR, that is X suffix AR. So in all the conditions of the load power factors, that is unity power factor, zero lagging power factor and zero leading power factor, in all the conditions of the load power factors, there is change in the terminal voltage due to armature reaction. So in all conditions, there is change in the terminal voltage due to armature reaction. So mainly the practical loads are inductive in nature. Mainly the practical loads are inductive in nature. Due to demagnetizing effect of armature reaction, there is reduction in terminal voltage. Okay, now this drop in the voltage due to interaction of armature and main flux, this drop is not across any physical element. Okay, here this drop in the voltage due to the interaction of the armature and main flux, this drop is not across any physical element. But to quantify the voltage drop due to armature reaction, armature winding is assumed to have a precipitous reactance. That is the assumption. Okay, this precipitous reactance of the armature is called armature reaction reactance. Okay, armature reaction, this precipitous reactance of the armature is called armature reaction reactance, denoted as XAR, ohms per phase. And the drop due to armature reaction can be accounted as the voltage drop across this reactance as IAR XAR. Okay, the value of this reactance changes as the load power factor changes. The value of this reactance, that means armature reaction reactance, the value of reactance changes as the load power factor changes, that is unity power factor or zero lagging power factor and zero leading power factor loads. So as armature reaction depends on the load power factor. Okay, thank you. So this is the explanation for the parameters of armature winding, that is armature reactance, so armature resistance and leakage reactance and armature reactance. Okay.